Okay, let's get started. So maybe before I jump into the technical material, let me just talk a little bit about projects since that's coming up. So the basic cadence is we'll have a midterm right before spring break, and then you'll go off to spring break, and then the week after spring break, basically you'll submit a project proposal. So you're supposed to spend your entire spring break thinking about projects. That's roughly the idea. Let's kind of a transition in the class. Historically, the project has been only open-ended. You kind of come with your big idea. We'll give you feedback on it. We'll try to make sure it's manageable, help you scope it right. And that's still true this time. But we're going to try to do something additional that we've not done before, which is to try to curate a handful of sort of challenge tasks. The reason is we have a Spot robot. I brought it in the first day. Spot's an awesome hardware platform. Traditionally, you haven't been able to actually write legged robot controllers for Spot. But they're just starting to open up the API. It voids all warranties, okay? But so I'm probably going to buy a new Spot at the end of the lecture, or at the end of the semester. But we have an opportunity now to start playing with Spot. And there's a couple ways we do this. Of course, we'll do it mostly in simulation. And even if you write just a great legged robot controller for Spot in simulation, the world will love you because everybody wants to simulate Spot. But nobody can simulate Spot because BD doesn't give away their low-level controller, right? So you can simulate the physics of Spot, that's easy. But if you actually want to see how it's going to walk around, or like if you're doing manipulation, you reach the arm out, the robot might shift its weight to counterbalance. If you don't have a model of that low-level controller, you can't use Spot in simulation to do higher-level control. So you guys should build some good controllers for Spot. I've done things like that before, so it's your turn, And but we're going to try to set it up kind of as some curated environments. We'll give you some of the standard challenge terrains. We'll give you a nice sort of simulation setup. And then depending on how many people are excited about this, we surveyed a little bit about this, but depending on how many people are excited, maybe we could even break things up, like have some people focused on footstep planning, some people focused on the RL version, some people we can potentially try to divvy it up a little bit. But first just tell us how excited you are about possibly taking that, as opposed to, I do quantum control for my PhD and I want to find Lyapunov functions for quantum control, or whatever, that's the other option. If you have a sort of a different thing that connects to your research, or you're just an idea that you want to pursue, that's fine too. Okay, so we'll give the logistics of that a little bit more, but I just wanted to sort of plant that seed that we'll try to, give you some slightly curated. I think if you go on your own, then the first step is sort of setting up the simulation, which can be a doozy if you haven't done that much before, right? You got a little taste of it setting up the URDF for the double pendulum. Depending on how ambitious you are, sometimes people spend a lot of time even getting to the simulation. So if we start with a simulation, you might be able to get a little farther on the control. That's the hope. Good. Saba, did I say enough about that? Is that, yeah? Good. Any questions? Yeah. I make it up each time, but the topics are going to be, the topics we cover, so it'll be drawn from similar it's kind of funny because I'm like, okay, this is great. I just came up with a new problem. And then I'll look at, I wrote exactly the same problem 6 years ago. Because there's like a finite well, I guess. But then I check, and I try to make sure it's novel. Okay, but. Good, okay. So the topic for today, we talked a little bit last time about Lyapunov functions, right? We introduced that. And the big idea I wanted to connect for you, and I'll say it again just as a warm-up here. Last time we talked about Lyapunov functions and gave the basic definitions, but we talked about it relative to the Hamilton-Jacobi, the dynamic programming view of the world, right? So I wanted to make strong the connection between the Hamilton-Jacobi kind of equations, which look like this, which, when you examine it for the optimal policy, looks like this. And that's finding that, it means solving an exact partial differential equation. And we relax that. You could relax it simply by turning that into an inequality. Okay, that's a good idea if you want to do approximate optimal control. We'll come back to that. But it turns out the only thing, you don't even need to be tight up against the cost. If you just want to make sure that the system's stable or that the task is successful, you can actually relax it even more and just say that we have some function that's going downhill at all. Okay? And that means, through the logic we went through last time, if you're going downhill for all x, you'll eventually get to the bottom of the hill, roughly. And although I focused on everything continuous time last time, I'll just, just for completeness, if you like the discrete time case, that goes through too, right? So in the discrete time, we had the min over u of Lxu plus j star f of xu. Okay, and you could write this, sort of the same thinking, you could call this like delta j star of x would be j star at the next x minus the j star at the current x. And that has to be negative L x u star in the discrete time case. And maybe you won't be surprised then to see that if you want to do Lyapunov in continuous time, then you relax that to just saying that the delta in V, after I take a discrete step, is making V go down. Okay, so I hope that sort of connection resonated, and we'll keep pushing on it. But the reason that connection's so powerful was my promise to you, right, which was that even though finding Lyapunov functions is hard, or finding cost-to-go functions can be hard, finding Lyapunov functions should be easier. Okay? So to make good on that promise, I need to give you some algorithms that actually solve Lyapunov functions and do a better job than what we did for the HJB. And that's what we're going to start today. Okay, and what's the intuition about why it's easier, right? So maybe I just write it down. So the promise, finding Lyapunov functions should be easier. And you could say, well, maybe finding anything that satisfies an inequality is just always easier than finding something that matches an equality. That's true. The intuition maybe is that the most important intuition is that while there is a solution, a particular function, which could be complicated, right, that for the cost to go, for V, there are many functions, right? Many, many functions you could pick from that could all prove stability of the system. And in particular, what we'll see over and over again is sometimes very complicated systems can actually be certified with very simple Lyapunov functions. Okay? The actual cost to go could be crazy and complicated, but maybe a quadratic Lyapunov function is fine. Okay? So that's the big win. Okay, so let's dig into that. And let me give you just a preview kind of the results. Maybe I'll write what I'm going to say or show. Here's a preview of the kind of things we'll do today. That's a system we could do with dynamic programming, but we'll start there because we understand it well, right? So the input to the algorithm is going to be the pendulum dynamics. And then a parametric family parameterized Lyapunov function. In this case, they're going to be trigonometric polynomial functions. I'll show you what I mean by that. For the Lyapunov. Basically, this means it's going to be a polynomial over the elements which have cosine theta, sine theta, theta dot, and powers of them. You could have cosine times sine, you could have theta dot times sine theta. It's going to be polynomial in those, which includes some trigonometric functions. Okay, that's what trig poly means. But basically, we're going to parameterize a candidate Lyapunov function, and then we're going to give algorithms that searches over those parameters, and the output will be the coefficients of the polynomial, the parameters, plus a certificate certifying that the Lyapunov conditions were satisfied for all x. Okay. So we've not had that before. I mean, we had it, I guess you could say we had it for linear systems because we could solve exactly. But for none of our sort of value or iteration methods could say anything about for all x that we were guaranteed to be correct. And that would have been hard because the optimal cost to go function might be complicated, right? We were always approximating with function approximators. But here we want to say, I found a function, right? And this function is absolutely satisfying the Lyapunov conditions for all x, up to floating point precision, maybe. Okay? And even that you can, if you care to get rid of the floating point, you can do that. Okay, and here's that example. The cool thing is, if you think about proving stability, this is just a passive pendulum, right? I want to prove stability of the point at the bottom. Now, remember what we did, how we did that before. We said, well, mechanical energy is a pretty good function. Whether we use that, and we'll prove that it has some properties. Okay, and it still had this foible, right, which was that we had to use Lassalle's principle to actually say that it was going to get there, you know, because the energy dot is less than or equal to 0. So we needed to actually say that we had asymptotic convergence. We needed one more argument. All right, so I'm just going to not go through the code here, but let me just show you the result. When I hit enter on the code and it solves instantly or whatever, I get this out. What is this? This is the eyeball of the pendulum, you recognize, okay. But one of those curves is the mechanical energy. The other one is the Lyapunov function that was discovered by the algorithm. I didn't put anything about energy in, right? And they're almost identical, okay? So it kind of discovered that that was a good function. But actually, it did better than the mechanical energy. It threw in a little term, so you didn't need to use Lassalle's principle. Okay, so it's actually going downhill for all the x. Okay, so you can see maybe I can make it bigger, but the energy has some coefficients. They could be different by a scaling. You have to be a little careful with the scaling because any scale of Lyapunov would also be a Lyapunov function, right? But I put in sort of an arbitrary set of these basis of these basis functions here, and then I searched for the coefficients, and the coefficients it found, matched the energy up to some scaling. Yeah. So I made sure that the terms that were involved in energy, or sorry, I guess I picked a naive set, but it is true that the terms that were involved in energy are in that set. But I picked one cosine theta, sine theta, theta dot, which is natural, and then I took all terms up to degree 2. There's a bunch of other terms that had zero coefficients that just disappeared, for instance. Yeah. In fact, you could probably, let's see, there's probably a few that are small-ish. Yeah, 0.007 or whatever. That term stuck around. That wasn't an energy, but that's actually the one probably that gave it a little tilt. So it was, yes.
How do you know what subset of terms?
I'm going to say pick everything for now, and then there actually are sophisticated tools that will allow you to down select what you need to pick. But for now, let's pick everything up to some fixed degree. Yeah. You could bring in something like that, but I think for a lot of the systems we're talking about, there's going to be a natural basis, which is rich enough. Like it's almost always going to be this basis actually: sine theta, cosine theta. If you have a n-link pendulum, you need cosine 1, cosine 2, cosine 3, whatever. You raise them all to a degree, and then you do some pruning, and you know that those are going to be sort of sufficient, or we'll see exactly what the sufficiency claim is. You could bring in Bayesian optimization kind of ideas to try to down select, but we won't need that yet. Okay, so maybe is that motivating? It's kind of cool. It's a simple example, but it's like pretty satisfying to have it like figure something out about physics and give like a certificate, which I'll tell you what that certificate looks like, right? For all x. We never had that before for anything interesting. This limitation that I'm going to talk about is, so in this claim, we're using polynomial functions. More generally, that's going to be like the linear neural networks kind of statement again. You can do this kind of thing with full neural networks, and people do. People do neural Lyapunov functions now. But it's very hard to get the for all x. Once you leave the linear neural network and you go to the for all x, or for the full neural network, then you end up only verifying things at sample points again. Except unless you have there's some small cases of neural networks where you can verify them for all x, but in general it gets very hard very fast. Okay, so if we stick in the sort of polynomial functions and maybe some forms of linear neural networks, then we can do strong things. The other thing that that's kind of like hopefully motivating. To do this right and to understand this for all x claim, we're actually this is going to be the lecture where we dive a little bit deeper into some of the optimization tools from the class, okay? So I'm going to introduce a little bit more of that pipeline. Some of you know convex optimization well, some of you haven't used it as much, so I'll say some of the basics before we get into the specific cases here. Good, let's jump in. And the question you should keep in your mind is, how the heck are we going to do for all x? And what is that certificate going to look like? All right, let's do a quick sort of optimization crash course, if you will. So I can introduce semi-definite programming, which we need for this. All right, maybe just even to say the basics. So, because it does get not complicated. Everything's simple as long as the notation is sufficiently clear. We all use the same language. Okay, let's just get our language straight. Okay, so this is when we write an optimization like this, f is a scalar objective function. And it's going to be we can only put a scalar up there, right? X are the decision variables. G are the constraints. This can be, each one is a constraint. We can in general have a vector of these constraints. This is a vector of decision variables. Okay. And in general, that optimization is arbitrary. Like you can have very complicated functions f, we could do all kinds of interesting things. And maybe if I'm trying to find the minimum value of x, that could be, let's say down here, would be the unconstrained minimum. Let's say the value here is the value of x that obtains the minimum is the minimizer. And this is, I guess, the minimum value is f of x star, right? But when I put constraints into the picture, then it gets more rich. I could say, let's say, I only want to consider, something that's like, I don't know, x greater than -3, x less than -1, something like that. And then maybe the constrained minimum here might be something very different. So that's just like a general. Does the green show up okay? Not the best choice, maybe. It looks pretty good up here, but this looks good. That doesn't look as good to my eyes. Yeah. A scalar objective. Let's put the green down. Okay, we've seen a few examples of F and G already, right? These kind of minimizations. We've done unconstrained minimization most of the time so far. But even when I write, min over even the discrete, some examples we've already seen, we saw like min over a discrete A of LSA. Right, that was the sort of discrete optimization where we just evaluated this inside for all A's and took the smallest one. There's really not a lot, unless there's more structure. But out of the box, when you see discrete optimization, you're getting, I shouldn't say that, but the way we've talked about it, you just evaluate them all. We also saw some cases where you could solve that min nicely, right? If we had on the inside, for instance, some terms that were quadratic. So you write it like this. We saw that case where you're minimizing over u. The objective was some positive quadratic, because R was positive, then we knew we had a nice solution. At the bottom of that. And we've also seen some cases where the objective, and I was lumping like all the terms that involve only x, for instance, I would just lump into those terms, right? From the perspective of U, the forms we've looked at had this kind of structure. And we also talked about linear things, okay, where the objective function maybe looks like this. Looks like this, but we never wrote that unless we also wrote some constraints on u, because otherwise the minimizer would be negative infinity. So like when we did the bang bang control for the minimum time double integrator, right? We put u between -1 and 1, and so therefore it obtained its minimum value down here, right? So those are the kinds of things we've seen before, and we're going to build on them. lot. So one of the key features of those two that I just drew is that they are convex optimizations, right? So let's just define that. We have a convex optimization if f of x is a convex function and the gi of x, the combination of all the gi of x, form a convex set. So a function is convex, be like this. A convex function is one that if I take any 2 points, I evaluate the function at those points, if I interpolate between those 2 points, then that straight line that interpolates them has to be everywhere above or equal to that function. Yeah? So what you want is that if I call this, let's say, XA and this XB, then I would like alpha times f of XA plus 1 minus alpha of f of XB, okay, has to be greater than equal to, because this is f of XA here, this is f of XB. I'm going to interpolate between them, where alpha is between 0 and 1. It's just an average. That defines the line between there. That has to be larger than the interpolation from the other direction. That's how you define a convex function. It's very simple. Yes? I put the curly brackets around spontaneously because I just wanted to be a little careful here, but you have many different constraints. What matters is that the total set that they define, when you take the union of all those, is a convex set. So a convex set is similar. It's if I have, for instance, a bunch of constraints in, let's do it in 2 dimensions then. So let's call this x1 and x2. Then if that's certainly a convex set, whereas know this intuitively, but just make sure we get the definitions right. So I can make things that are not convex sets. And in fact, the definition is the same. It is the same. It's that basically if you take any 2 points in the set, that the straight line that connects them is still in the set. Okay? And you can write the same thing with the interpolation of alpha. In fact, they are exactly the same definition. It looks like there's kind of like case 1 is a function, case 2 is a convex set. The way to unify those in your head is actually the epigraph of the function is a convex set. That's all it means. the area above the curve has to satisfy the definition of a convex set. Okay. Why do we like convex optimization? Maybe it's obvious or intuitive here, but when we're doing general optimization, if you're using gradient descent or something, maybe I'm coming from this side, I'm going to worry about getting stuck in local optima, right? And it's very hard for me to guarantee that my solver finds the very best global optima solution, right? And convex optimization, loosely speaking, are the class of optimization problems that have no local minima. That's again, a class of optimization problems that have no local minima. There are other bigger classes that still have no local minima. Yeah.
Why do we also care about?
Yeah. So imagine you're doing gradient descent, okay, and I'm walking from some solution here that's feasible, and the actual optimum here, if I were to look out of the board, I'm walking here, I could get stuck in a minute. Maybe it's, that's maybe not a great example, but you could imagine getting stuck in a, this constraint. In the extreme case, you might even have disconnected, maybe my constraints say something like you're in this set or you're in this set. If the optimum's over, here, and you're currently going here, you're going to get stuck. Right? So in order to have a chance of finding the global optimal solution, you want to have both the constraints and the objective function well behaved. So that's a very general statement. There are important classes of convex optimization for which we have really good solvers, basically. Okay, it's one thing to have the property in principle. There's another thing to be able to have all the properties you need to basically make a great interior point method and a fast solver. Okay, so the classes that are most famous, you'll hear about linear programming. That's when you have linear objective and linear constraints. So this is typically written C transpose X, let's say, minimize C transpose X subject to like AX less than or equal to B. Would be the union of a bunch of linear half-plane constraints, and that can describe convex polyhedra like that. And we cleverly had you struggle a little bit with LP without fully defining it on one of your p-sets to set you up for today's lecture. Okay. You've probably heard about quadratic programming. It's another super important class. Which has quadratic, this is convex, so positive quadratic, convex quadratic. Typically, when you say QP, you mean the convex quadratic QP, objective, and still only linear constraints. Okay, that's a workhorse for balancing humanoids. Imagine doing LQR, but having a few constraints, like you can't pull on the ground. That's where you get QPs come out. It's a slight generalization of LQR, but it can handle some of the constraints we have in real robots. There's a few more really important ones. We won't say anything today really beyond just mentioning this. There's a second-order cone programming. It sits in the hierarchy. So as we go from linear programs down, we have like super scalable, super fast, super robust solvers. And as we go down, they're going to get they're computationally a little bit more complex. Still super scalable, super fast for QP, but a little bit harder than LP. SOCP, it starts getting, harder problem again. And the one we'll use a lot today is semi-definite programming. So second-order cone programming basically adds the ability to add ice cream cone-shaped constraints. You could say I have a constraint that is formed by potentially a rotated, whatever, but ice cream cone set. Yes?
Does the convex set need to be in the real numbers so the linear programming wouldn't count?
So integer and linear programming is not a convex program, so you're right. So this is all assuming real numbers. Yep, good question. But that's a super important class of optimization. It just brings a different set of tools. Yeah, and then the one we'll use today is semi-definite programming. Okay, so typically this is stated as a linear objective. You can have linear constraints. And you can have positive semi-definite matrix constraints. I'll make that precise when we get a little bit further. Okay, but roughly you're allowed to say that some linear combination of the decision variables are form a positive definite matrix. Okay, so with that in the back of your mind now, or the forefront of your mind, but we're going to think what are the, from this well of tools, what are we going to start using to try to find Lyapunov functions, okay, and give a certificate that they work for all x. That's the puzzle for today. The reason I'm just being a little bit more specific with LP and a little bit more vague for now here is because we're going to be able to do a little bit with LP. We'll start there. Okay, we'll give you the core idea with linear programming. But to really get the certificate for interesting systems, we're going to get to semi-definite programming. Okay. Yeah. This is, by convention, a linear objective, linear constraints, plus SOCP constraints, ice cream cone constraints. But it's actually strictly any QP can be solved with an SOCP, as an SOCP if you wanted, because you can always take the quadratic objective and put a slack variable in and solve it as a second order cone constraint. So it's actually a strictly bigger class. And similarly, the semi-definite programming can eat second order cone programs and everything above it. But by convention, when you call a solver, you only handle linear objectives. How do we compute Lyapunov functions using these kind of tools? All right, so the first idea is we're going to parameterize the Lyapunov candidate. Oh, by the way, some of you have seen it, but if you haven't, Drake does have, the tutorials across Drake are at various levels of readiness. I would say the mathematical programming tutorials are the most detailed. And they, you have a general, like how do you use mathematical program, but there's specific examples of linear program, quadratic program. Arbitrary nonlinear program, sums of squares, and semi-definite programming is what we're going to cover today. So if you want to sort of more details about any of those structures, on how to use them, that's kind of one way to do it. And I can give you great references, and I put them in the notes. There's lots of good material online for convex optimization. We're going to mostly, we're going to be heavy users, but you can get by without understanding all the machinery if you understand the abstraction that these tools provide. All right, so we're going to parameterize a Lyapunov candidate. So let's say I have a dynamical system equals f of x. Let's choose v of x as some combination of nonlinear basis functions. Right? Call it a linear neural network, if you will. We'll restrict ourselves later to polynomial basis functions, but for now, these are arbitrary nonlinear basis functions. Okay, so it's not like we have to come completely out of thin air in sort of or non-parametric way or something. We're going to actually just parameterize candidate Lyapunov functions, like in my motivating example. And then we're going to formulate this as the search over alpha to find something that satisfies all the Lyapunov conditions. Okay? How do we use convex optimization? Do you remember how you did it for the linear programming, dynamic programming as linear program problem set? I know there's always a danger that you could accomplish the problem set without fully grokking the lesson. Wait, it's very hard to like introduce something that big and ask you to fully grok it, but maybe you got the main point there. The linear programming version operated on sample points. Okay. We did the same thing in dynamic programming, but we'll do it for the Lyapunov case. Okay. Draw a bunch of state samples xi, and we're going to just ask that the Lyapunov candidate satisfies all the conditions at those samples. Right? That fits immediately and beautifully into linear programming. And it's actually pretty good. Okay, so you might say, I just want to find any alpha subject to, let's make sure that somehow it's actually 0 and 0 in case we were sloppy picking the xi's. And then for all xi, we'll say that v of xi is greater than 0. Maybe it's, if we want to be fancy, we could say it's greater than something that I know is radially unbounded. Okay? But from the purposes of the program, right, this is sort of alpha transpose phi of xi greater than epsilon xi transpose x. That's just a linear constraint in alpha. Right? Similarly, we want v dot 0 equals 0, v dot xi, and let's remember that's just partial v partial x, f of x I, right? Maybe we want that to be strictly negative. Okay, if v was alpha times partial times phi here, then actually v partial x also has a similar form. This is alpha transpose d phi dx f of xi. Still linear in alpha, right? Okay, if you just put that into your solver, what are you going to get? The great thing about a convex optimization solver is if it can find an alpha, that satisfies all these constraints, it will tell you that alpha. If it's not possible, it'll say infeasible. Right? It's just it's kind of a yes or no answer. It's very satisfying. It's not like, also maybe cleverly timed. We got you like struggling with pendulum continuous value iteration curves that go down like this or whatever. It's not like that. It's just yes or no. It worked or it doesn't work. Right? It's not gradient descent, tuning parameters, whatever. It's just bam, it's done. Here's the answer, or bam, you asked a bad question. Right? No solution. Okay. This one, since I left a lot of freedom, it has a lot of freedom to possibly pick the v's that satisfy this. Right? It could pick maybe a very small v that was just the right shape. It could multiply that by 10 and get another v that's much bigger. So I don't actually, that kind of offends me as like an optimization person. Like I think you haven't fully specified the problem. You left the solver a little too much freedom because it'll probably pick something like very close to 0, for instance, right? It'll be like out of time. So I would tend to actually, instead of having it a feasibility problem with no objective, that's when I write find alpha, that just says there was no objective. I would typically say something like minimize over alpha, something like v of xi, v dot of xi minus 1. Let's say I want it to be v of xi to be approximately 1. And if I want it to stay in an LP, I'll do it in the L1 norm. Okay, but you can write this, you'll see it in the code if you look. You can basically say, I want v dot to be, among all the v's that you pick the one that's going downhill at about the rate 1. That's like, that means v would be something like a time to the goal. Okay, just, all other things equal, give me one that's going downhill at a reasonable rate. Okay, so I've coded this up. It's a simple LP based on sampling. Okay, this is the pendulum example again. You see my basis functions here. I just wrote the basis function 1. I made it vectorized. That's why I have to multiply 1 by 0, or whatever. Sine, cosine, and then I just made a stack of bases. 1, sine, cos, theta dot, sine squared, cosine, sine, cosine. I didn't do cosine squared. Don't need that one because I already had 1 and sine squared. So cosine squared is covered, right? Okay, and then, but otherwise, all of the monomials up to second degree. And then I take my sample points. I just made some uniform samples across the grid. I evaluated the derivative at those sample points. I made my mathematical program, added some linear costs and constraints. Okay. And this does almost exactly the same thing as I did with my beautiful, the example that I like most, which is the one that has a certificate. This one does the work. It just doesn't have a certificate. And why is that bad? Or like, I don't know if I picked enough sample points. It looks like, to my eye, it looks like I picked enough sample points. But I really don't know. I don't have any guarantee that I chose the right sample points, chose enough of them. And actually choosing sample points in high dimensions is to be avoided, I think. It's better than having to put a uniform grid, but you really don't know what, the mileage may vary with this. But that basic idea of I'm going to parameterize a Lyapunov function. I'm going to write these Lyapunov conditions down as constraints, and then I'm going to search over alpha to find the Lyapunov function. That's today's recipe. So ask me questions. Does that make sense? There's 1 year, everybody's like, says do thumbs up, thumbs down, or eh. What do you think? Thumbs up, thumbs down? Does that make sense? Somewhere in the middle, a lot of sideways thumbs. Okay, yeah? Yes.
Just a scalar.
Correct. This is just saying, so I could have just put a 0 here, but I said, don't just be 0, be bigger than something that's going up at some small rate. And the reason to do that is then I can say, if I'm talking about global stability, I could say it's radially unbounded. Yes? Similarly, I just want to make sure that it's absolutely less than it's absolutely going downhill. This would be the difference. This gets into some of the subtleties of, so it's called semi-definite programming when we get to it, or the linear programming is actually less than or equal to. Okay? So if you want Lyapunov in the sense, if you want stability in the sense of Lyapunov, then you have it with 0. If you want stability, asymptotic stability, that you want to be going down. And if I would put the V over here, then I could get exponential stability. So think of this as a version that's giving me asymptotic stability instead of ISL stability. Yeah? Yes?
I'm not sure about the shifting V dot by 1 part.
So this is the objective, right? This can be a linear objective. It looks a little funny, but I promise you can make it a linear objective. Okay? This is just saying, of all the alphas you pick that satisfy these, because I know there's an infinite family of them, pick the one so that the sum over all the xi's, v dot is normally around -1. Good catch. -1. I want that to be close to -1. Yes?
If you sampled like the upper fixed point, then it affects 0. Would that break your constraint for the going downhill?
Yes. Nice. Good. So if I happen to sample the upward fixed point where it couldn't go downhill, and actually that was kind of that was embedded there because this is the point that sampling doesn't give me a guarantee, right? So there is actually a point that I know about in my state space that the sampling didn't find, naively, that would have violated those constraints. It's the upward fixed point. It's not going downhill at the upward fixed point. I shouldn't be able to prove absolute global stability to that downward fixed point. Nice catch. Okay. It turns out for the one that has a certificate, of global stability, how did I do that? I intentionally held out the upward fixed point. I said it was less than something that included a sine theta squared. I'll write that when we get to it. But there's a way to do it precisely, but you have to say I'm stable to the set of possible points, including the upward fixed point. Nice catch. Okay, there was still a lot of this, so more questions are fine. Yes?
I'm just trying to, so there are these techniques which I use for learning dynamics from data, like Cindy and
Sure.
this seems very,
Seems like an earlier version of Cindy. I think of those as solving very similar, different problems. Certainly, there's some linear parameterizations and stuff in Cindy. I see that. Cindy is it's a system identification of sort of a model order reduction idea that's based on by Steve Brunton and company. That's true that you choose dynamics, you parameterize them similarly, and you choose your basis functions in the standard way. But the concept of Lyapunov isn't available in Cindy, or it's not an explicit goal, right? That is really about learning dynamics. I think there's a handful of core problems in control, like sysid is one, stability analysis is another, feedback design is another. But there's only like 4 or 5, and that's a different one for me. Yes. Okay. So this is so the solvers consume specifications of the form less than or equal to. If I wanted to have something that is written in terms of less than or equal to, and say that it was strictly positive or strictly negative away from the origin, then I can add this sort of small term, and I want some positive function that's going out. I could have just said, if I just cared about it being positive, that would be okay. But I know it has to be 0 at 0, so I put this in additionally to make sure that 0 at 0 is still a satisfying solution. And it happens that choosing something that I know goes nicely to infinity, it also gives me radially unboundedness. Maybe that was the piece I should have said before, was that why would you not just use epsilon? Yes? What you say is not wrong, but it makes it sound magical, and I think there are principles that give you the right answer most of the time. So I think, let's see, this is a very standard choice. Having seen it, I think you will probably use it again, and you don't. I think there's a little bit of being clever, but I think there's a handful of standard choices. And in particular, maybe to convince you, I think we can get to the point where we have code, like we have a region of attraction code in Drake, where you just hand it a plant, and you hand it a rough Lyapunov candidate, and it does all the setup for you. So it's not like for every new system I had to be clever. There's like standard enough answers that you can give me any system, and I'll try to operate on it. Yeah. Okay, I'll keep going, but ask questions if you have. Just to make one point super clear, I think it is, but what are the decision variables in this Lyapunov problem, right? It's easy to think about optimizations over Lyapunov functions and think maybe the decision variables are x, but they're not x. The decision variables are the coefficients, the alpha of the Lyapunov function, right? That's going to get a little bit more subtle when we go to for all x, okay? So just lock that in. The decision variables here are alpha, not x. Nonlinearities, complexity in x, but simplicity in alpha. Okay, that's what gives us some mileage. How the heck are we going to turn it from this sample point argument? Oh yeah, go ahead. Yeah, this is a great question. So to say it again for the microphone, I guess. Can we say something, for instance, if a system is known to be stable, are we going to be able to guarantee that this finds a stable Lyapunov function in the limit of even infinite samples? So that's a great question. The first gap is that you have to pick a basis function, the basis functions for V. So there are stable systems that, let's say even stable polynomial systems that don't have polynomial Lyapunov functions, right? They're really hard to find, but papers have been written about finding them. There's systems that have this. So there are some gaps. That's one of them. I think in the LP form, in the limit of infinite sampling, then I think that would be tight in the next level. If it existed in the class of parameterized Lyapunov functions, it should find it. As we go forward on the certificates, there's going to be another gap that enters. But the takeaway message is those gaps are small. This is almost always going to work. That's in the practitioner's view is don't mind the gap. That's probably a bad lesson to live by. But. All right, so how the heck are we going to do for all x? Like, what chance do we have? We have this, like, searching over alpha, but we want to write a finite number of constraints. We don't want to write infinite constraints. How can we possibly do better? Well, here's the core of the idea, okay? It seems fancy. It's pretty simple, okay? For V, it's really simple, okay? Why don't we just parameterize V differently? Like, why not do that, right? Just take a linear combination of positive functions, and then I know V is positive. That one's easy. V dot's going to be harder, okay? But actually, that's most of the work. So, and I could similarly put like constraints, of course, that alpha is positive. Right? If I have positive combinations of positive functions, then that's going to be always positive. Satisfy those conditions nicely. That's not quite right, actually. That's not quite the way you want to write this. There's a generalization of that. Right? So what you really want to write is what I really want to write is this. Okay, that's just a strict generalization of this. So take, this would be v1 of x, v2 of x, vn of x. To be positive definite, it's going to be symmetric, so I'll call this like alpha 1, alpha 2. I'll write alpha 1, 2 here, alpha 2, 2. It's a symmetric matrix, right? It's just a quadratic form. So the conditions that all of these need to be positive, that's too much. You don't need that. What you actually need is that this matrix is positive definite. That's less constraining than saying all the elements are positive or all the diagonal elements are positive. Okay? Why do you know that that's sufficient, right? So G of x, just that, if you have a PSD matrix, G, for instance, that just says, the definition of that is that for all x, x transpose G of x greater than or equal to 0, right? That's just what a PSD matrix is. And so certainly that implies that since any x is there, this must also be true. Right? So that's just that. In fact, that's the right generalization. Okay, so this idea is really good. We're going to use it, but we're going to use it in this one. Okay? Parameterize yourself positive definite functions. So that'll work for V, okay? But how about V dot? V dot of x looks like partial V, partial x, but it has f of x coming in. And f of x is whatever physics gave us. Right? So it's a little bit harder to parameterize that to be arbitrarily negative in that case, right? Unless it turns out, there's a good trick, okay? What if you said, here's some other function f. Okay, and I'm going to choose it to be parameterized like this. Okay, maybe I'm going to do the negative one for v dot, okay? Okay, with g2 positive. Let's just say I've got some other function that I'm going to parameterize to be by construction negative. And what if I can say that v dot x equals x for all x? If you can do that, which you can do that in some cases, okay, then that's going to be the trick that's going to get us v dot. In particular, there's going to be classes of f and v. Polynomials are the most famous one, where I know how to pick the bases here, so that making f equals x, v dot for all x just means matching the coefficients of the polynomials. And those are going to be linear constraints. Okay, so I'm just planting that seed, and we're going to come back to it. All right, but this is the rough idea. We're going to write functions that are positive by construction. The super cool thing, and the reason it fits into the convex optimization hierarchy, is this constraint of having a matrix be positive definite, positive semi-definite. That's a convex constraint. Right? The set of positive semi-definite matrices forms a convex set. You take positive semi-definite matrix 1, positive semi-definite matrix 2, take a linear interpolation between them. Every matrix in between is also positive semi-definite. That's like a two-line proof, but okay. So the class of semi-definite matrices is a convex set, and we're going to have good algorithms for searching over that. If you can write something saying I've got some decision variables that must be positive semi-definite, and then only linear constraints, back to my other decision variables that I care about, then you can write that as a semi-definite program. Yes? Just a coefficient-wise. Yeah. Good question. Good question. Yes? Yep. So, yeah, I guess I'm being a little sloppy about it. It's going to, so all of them have the solvers actually enforce semi-definiteness. If you want to make positive definiteness, you do these kind of that trick where you just say greater than, let's say, x squared, okay? And then, again, the Lyapunov conditions are precise. If you have strict definiteness, you can say something about asymptotic stability. If you have semi-definiteness, you can say something about ISL. So I tried to be careful about it last time, but I admit I'm being sloppy about it this time. It's mostly because the solver tolerances are kind of like, it gets a little bit more nuanced. So one can make careful statements about these things. Yes? Because we're going to put a lot of costs and a lot of constraints together, and then we're going to ask the optimizer to solve it. In the case of convex optimization, I know my solver is going to find a global optima. Right? That's the place where I know my optimization is going to work if I can formulate it into a convex form. Okay, so let's use this trick to find the Lyapunov functions and verify them for all x. Oh, sorry, yeah. That's a fair question. Okay, so convex optimization feels limiting. I think in this class of problems, and the reason we emphasize it during the Lyapunov lecture, is because you can search over simple functions, even for complicated systems. You can often find simply parameterized functions, have convexity, and get go a pretty long way with that. It was less of an immediate topic. We can do some approximate dynamic programming with it, but that would be a harder class of problems, and convexity hasn't penetrated as deep there, right? But this Lyapunov, where there's a whole nice family of functions to search over, we can live in this space. Now, I would say one might summarize my academic journey as trying to find convexity in the hard multi-body problems. So it's a labor of love sometimes, but it's a good exercise. It's a good profession. I like it. Okay. It seems like people can see a little better here. So. All right, let's see how that plays out for linear systems, where it's like super clear. And then from that example, I hope you saw that we're going to be able to extend it to nonlinear systems. Put this up so we can look at it. Think back to it. All right, so let's say we have x dot equals ax. Is it stable? Now, a savvy engineer would take its eigenvalues, okay? We're going to do something way fancier than that. Because the generalization, which uses semi-definite programming, is going to have extensions that taking eigenvalues won't give you. You're going to be able to talk about robustness and other things that you just can't get from an eigenvalue solver. Okay? So the idea here is let's parameterize v of x as x transpose p of x, where I want p to be like this. Okay? V dot of x is going to be 2x transpose p a x, like this. But that's a scalar. So you'll never see it written like this, because this is not symmetric by default. I can split that up. I can take that 2 and split it up and write it as PAX plus X transpose ATPX. Right. Now that's symmetric. It's a scalar, so you didn't change anything. Okay, so v dot of x is less than 0 if the inside of this, PA plus A transpose P of x, is a negative definite matrix. This is the famous Lyapunov conditions, for linear systems. Actually, to your point about completeness of the algorithm or correctness or whatever, there's a lot that's known about this for linear systems. It turns out you don't actually have to solve a semi-definite program for this either. It turns out if a system is stable, then you could say you can pick any q greater than 0. This is just an aside, sort of on completeness, but it's good to know. You pick any q greater than 0, and then solve PA A transpose P equals negative Q. And you'll be able to find a P if it's stable. So you can search over all P's that are negative semi-definite, or you can just pick one by choosing some Q. Okay? That's a nice extra property we have for linear systems we don't have in general. This is I wanted to write that because this is called the Lyapunov equation. If you hear the Lyapunov equation, or you call Lyap in MATLAB, it's solving that equation. Yeah. Okay. So now this is interesting, right? So Now I can say, I can write a semi-definite program, find me some alpha such that P, which is going to be parameterized by alpha, right? Alpha 1, alpha 2, alpha 2, 1, okay? Such that P is greater than 0, and P A plus A transpose P is less than 0. This is the kind of thing we can solve with semi-definite programming. This one clearly is a positive definite constraint. This one doesn't look like a positive definite constraint. It looks more complicated than that, but it can be a positive definite constraint. Precisely by the trick I just sort of alluded to, maybe I'll make an extra set of variables, say alpha and beta, so that I have P greater than 0, and this will be the one parameterized by alpha. And I'll do P2 parameterized by beta, okay? And I'll say P2 greater than 0. And then I have a linear constraint saying that PA plus A transpose P equals negative P2. Those are all linear constraints. So even though that looks like more than just asking for a matrix to be positive definite, it can be converted with linear constraints and a few extra decision variables into just a simple form. And that's actually exactly the trick I just sort of alluded to up here, right? Let's make a second function, make it positive definite by default, and then set it equal. Okay, so that's exactly what we do in the linear system case too. Yes? Yeah, we don't like to talk about that. No, it does. The SDPs do get big. Okay, I think for this kind of problem, it should be fine. But it is true that there's a recipe for making SDPs that ends up generating lots of SDPs, and problems get big. Yeah, but neural networks are bigger. Any other questions? Okay, let me end with the motivation behind that here was to do more than just what you could do with eigenvalues. Okay, so let me give you an example of like what you can do that you couldn't have done before. Let's do robust stability analysis. The first example. Okay, so I'm going to say I have x dot equals a of x. I want to prove it's stable, but the coefficients of a are unknown, are uncertain. Okay? Now I have to choose some description of what I know about a. Okay? So what I'm going to say is that a is, I don't know, it's between 1 and 10, or it's between 3 and whatever. I'm going to give some sort of description like that. The elements of A are all between 1 and 4. Okay? The way I'm going to write that is I'll say that A is a linear combination of other A matrices. So it's sort of like if you have a bunch of A matrices in the coefficient space. This is like a vertex description of the polytope that defines possible A matrices. I'm saying any A matrices that are some sort of, can be made out of a linear combination of, a convex combination of those. Okay, that's like, some way for me to say, I don't know. I don't know A, but I know it's somewhere in there. Okay? The mass could be between 10 and 12. if you can find me, I'm going to abstract this to find me a p greater than 0, such that for all I, PAI plus A transpose I, P is less than 0, then you've done something pretty cool. So first of all, let's agree that this is still a semi-definite program. Okay, these are all just semi-definite constraints. But what's cool is this says I found a single Lyapunov function that if my system is this system, it's going downhill. If it's this system, the system's going downhill. If it's this system, it's going downhill. Okay, for all of the points on of the convex hull. And it turns out, because of linearity of everything, this also means that everything on the interior, so you can just work the math through to see that this actually implies that that is true for this thing. Okay, so if you're able to find something that proves that all the vertices are stable with the same Lyapunov function, then the every set in the inside, every A matrix inside the interior of that is also stable. It's a simple, small SDP, okay, and it can prove robust stability. And you couldn't have done it with eigenvalues. They're not easily. Yes? It turns out that if I just take any AIs and I'm allowed any linear combination, then putting an AI inside would be fine. This takes the convex hull. Yeah, think of this as taking the convex hull. Yeah, so that's actually robust to that. Okay, I have it all coded up, of course, but we're out of time, so I won't run it. Here's a gap. Okay, so if you have a system for which a set of A's that are all stable, if you find a P that stabilizes all of them, a common Lyapunov function, then you have a guarantee for all X that they're stable. But it is possible that all of those A's are stable, but it cannot be proven to be stable with a single quadratic common Lyapunov function. Okay, so actually when I run the code, I make like random A matrices, like stable A matrices, okay? And I run this, and like, I don't know, 50% of the time it fails. But that's like way harder than real life, right? I mean, real life doesn't have random matrices that are barely stable. It has robots that, well, fall down dramatically or hopefully stay up, right? But just there is a gap there. That's a good stopping point. So we did a lot. We did a lot, right? So we're doing for all X by using quadratic forms, and we're going to bring it back to the for all X of nonlinear quadratic forms next time.